We are now recording. Let's start from this one first. Just a little bit of review, because we're starting with example 4, and just a quick review. First, now what I'm going to do, we did this last time, I'm going to do it again. I'm going to wait till the end of class to make all the announcements, because otherwise I'll make them now and then more people come in, I'll make them again, just sort of redundant. So before the first one of you has to leave today, give me a few minutes notice and I'll make the announcements then, and hopefully we'll catch everybody, okay? So before you have to leave, give me a few minutes of warning so I can stop and make the announcements, and then I'll go back and wrap up. Okay, so that said, any questions on anything we've done so far? All right, where we were, this is in chapter 19, which is alternating current electricity, and we're on page 531, and this happens to be under 19. I'll put this on the page. 19.1. I thought we got into 19.2. We're in 19.2. Okay. Now, this is just a review here. This is what the problem is based on. This is a transformer. Now, a transformer has to have an alternating current source. Transformers like this do not work on DC current. There's no way it can work. Okay? Now, alternating, what that means is the voltage goes up and down and up and down and up and down constantly. I mean, as in very, very rapidly. Oh, wait. I just remembered what I forgot to do. I wish I had done this before I turned everything on. I did it for 1 or 2 people, but not everybody. Sorry about this. Going to have a little bit of delay here, because I want all of you to have, if you have any tests that you need to turn in, I need those now. Okay? Okay. Here are your tests back. And just in case, there are some people who may come in late or who may try to get it to me later. Please don't let anyone see these answers, because it may be that'll make them have a good grade and cheapen your grade. We don't want that to happen. Okay? Because there are some that haven't been turned in yet, but they're not here. So I don't want it to diminish your grade at all. I'm going to give Tiffany hers. He is not here yet. Deidre won't be here. Jordan is not here yet. So there was test 1. Here's test 2. Katisha's not here yet. Kayla is. Kira is. Sashi is. Julia is. Where y'all sit alphabetically. Okay. Cece is. Okay. Bottom part of the alphabet didn't come in well today. All right. Test 3. Kira. Asi. Lydia. They were not here. See. Here. Okay. All right. Test, whatever, 4 maybe. Kayla. Kira. Stasi. You can tell the people who are usually here and turning into work, they're still here. CC. Kira. Deidre. All right. Now, I'm missing, start of the next one. Missing a next test Do you have your electricity test yet? Huh?
Can I turn to you by the invoice?
I can't hear you.
Can I turn to you by the invoice?
Yeah. Okay. So that'll be fine, but there's not many of them have been turned in, have they? Okay.
Test 4, did you already put in Blackboard?
I'm sorry?
Have you already put test 4 in Blackboard?
No. Well, I don't know. I haven't been able to get on Blackboard in about 2 weeks. Okay. So anything that's been turned in since then, no. Okay. So, sorry, I meant to get those to you earlier because I said I would first of class, and then I got to do it. Okay. Let's get back to our transformer. Has to be alternating current because you have to have a changing current to induce a magnetic field. Okay? And that's exactly what is happening here. The alternating current going through this coil, and the more turns you have of the coil, the stronger the field, right? And the stronger the field, the more it's done, the stronger the magnetic field is created. And then that creates, over here, a changing field, and the changing field induces a current. So you see, changing electric current induces a changing magnetic field. The changing magnetic field induces a changing electric current. So you have an AC current coming out here. Well, what's the deal here? The more turns, the stronger the field. So this creates a very strong magnetic field, but this has fewer turns here, so it comes across with a lower field. But the power is the same. And power is voltage times current. So when you do more voltage here, less voltage here, a lower current here produces a higher current here because the power is equal. Okay? So that's what's happening. So here is the basic formula. The voltage in, which we usually call V sub P for primary, over N sub P, which is number of coils here, is equal to V sub S, secondary, times N sub S. Okay? So those ratios are the same. This has a bigger number of coils. It produces a bigger field. This will, fewer coils produces a smaller voltage. But, of course, that will produce a larger amperage. So that's what we're based on. Here's another way. This is what we call a step-down transformer, just like the other one was. There's not much difference here. The magnetic field induced by the core, by the primary circuit, then the voltage induced by the in the secondary coil by the changing magnetic field in the core. So, same thing we just said, just another slide of it. This, of course, is a step-up transformer because you have fewer coils here, so it increases the voltage coming out of the secondary coil because there's more turns there. This is a step-down transformer because there's fewer coils on the secondary side than there are on the primary. I guess that slide was on the next page, isn't it? I'm sorry, I got ahead of myself. No, where it is? Oh, there it is. Okay, let's go back. Yeah. Okay. All right. So now we're ready for example 4, bottom of page 531. All right. A transformer on a neon sign has 100 turns on the primary coil and 15,000 turns on the secondary. Let's use this picture, okay? That one will fit a little better, even though it's not one where we are. So what we have here, 100 turns on the primary coil. What would represent that? What symbol do we use for coils on a core? What's the symbol for it? It's N sub P, exactly. Number of turns, primary side, and that happens to be 100. And the second zero is significant. 15,000 turns on the secondary coil. What would that be named? N sub S. The number of turns on the secondary side is 15,000. Okay? first zero is significant. The other two are not. Okay? If the voltage applied to the primary coil, what would that be? V sub P is equal to 110 volts. And that zero is significant. Okay? What will be the secondary voltage? So what are we looking for? V sub S. Okay? That's the unknown. How would you approach it? Okay? You're going to use V sub P over. Okay, you can do it that way. V sub S is equal to N sub P over N sub S. These are direct proportions. That means they have to match up. You could either do V sub P over N sub P, V sub S over N sub S, or V sub P over V sub S, N sub V sub P over V sub S equal N sub P over N sub S. Or you could put the S's on top. Or you could put you can rearrange them anyway, but the order has to be equivalent on both sides. Okay? So now let's plug and chug. This would become V sub P is 110 volts. Okay? Over, we don't know, V sub S. All right? Is equal to 100 over 15,000. I guess I'll put my bars there. Now, how do you solve a proportion? Anyone know? Second? Cross multiply. Okay? So I like to do one with the variable first. That would be 100 V sub S is equal to, whoa, pull out a calculator, somebody. 165 with 4 zeros. Is that right? Is that right? 165,000,000. 1,650,000. That's sort of big. So what we're going to do is divide both sides by 100, which is really pretty easy to do by just slashing out two of the zeros. And that gives V sub S, believe it or not, is 16500. 16,500 volts. Whoa! Talk about a step-up voltage. That is big. Okay? Now, let's see if they got the same thing before I do too much bragging about it. Yeah, 16,500 volts. If we wanted to use a smaller number but a bigger unit, what would that be? No. Move it 3 places. That'd be 16.5. Oh, I know what you're doing. Okay. You were right. Okay. 16.5 kilovolts, or you are doing 1.65 times 10 to the 4th volts, right? Yeah. You were doing scientific notation. I was using a smaller number, bigger unit. Okay. 16.5 kilovolts. That's big. But again, too, neon signs are high voltage, low current. Okay. I assume. I've never messed with them. All right. I've already talked about step-up and step-down transformers. We saw pictures in the text. So the next figure on the slide set is the one on page 535, which is right at the end of the chapter, or section anyway. So let's go back and see if there's anything else we need to glean here. Now, they make some statements here which are really good. Talk about auto transformers. I think that means automatic, not automobile, but I don't think that's really all that significant to you, so I'm going to not mess with that much. Then they talk about energy losses in transformers. Energies do not create energy. The energy stays the same. If anything, it loses a little bit. They bump up voltages, which drives down current, or they bump up current, which by driving down voltages. However, there are some losses that are involved. Copper losses. These result from resistance in the copper wires in the core, and they're unavoidable. Those coils having 15,000 turns, that's a lot of core, so there's going to be some line loss there. Remember, the length of the line contributes to the loss. Okay? Copper minimizes that, but it still doesn't eliminate it. Magnetic losses, called hysteresis losses, they use that word in medicine too, right? Some energy is lost, turned into heat by reversing the magnetism in the core. That's being reversed at 60 times a second. I mean, it's really fast, so it does produce some heat. Now, let's think about that for a moment. This is sort of sad. I think I've got this right. I'm not absolutely certain on it. But engineers, industry people wanted to minimize that. Well, they came up with a fluid, and if I'm not mistaken, this fluid is chlorinated biphenyls or something like that, CBVs or something. There's some sort of a really complicated organic sound title. And they found out this worked great in these transformers by reducing the heat loss, okay? So they started manufacturing this stuff and pumping them full, and it was a great win for the industry. Of course, where they manufactured it, they'd have some waste, and these are pretty complicated, like chemicals, and they would, wash out their tubs and dump the water and these kinds of things. Well, it turned out after many years, they noticed people started getting cancer in these areas. And strange cancers, unusual cancers, and lots of them in areas. My wife works as an epidemiologist studying diseases, and they call this clustering. And they said, why are there clusters of cancer here? They started looking into it, and then they discovered these chlorinated CFCs, fluorocarbons. I think that's what they were. Some sort of a combination of things like this were cancer causing. And here this company had been dumping, cleaning their vats, doing all this kind of stuff, letting the water run into the sewage lines. Downstream from them, here live people, unfortunately, in the lower rent housing, which of course meant disadvantaged people and generally that couldn't afford the nicer areas, and their kids played in these ditches, and they used water from the ditches to irrigate their gardens, so they were eating the foods coming out of this, and they were getting cancers. But it took a generation for people to discover that. There was a big lawsuit, and I think they're being cleaned up now, but the company, of course, sold out, so it wasn't responsible anymore, and it's been a big legal hassle. That happened, if I'm not mistaken, that happened in Anniston, Alabama, at the Monsanto plant. When I was in between jobs, I got an opportunity to do, because of my soils background, to do soil sampling at that. We were on one side or the other of the lawsuit. I don't know which side we were on. I think on the plaintiff side, but I'm not sure. And we were doing sampling so they could measure and see what the levels were. Okay, and then there's another thing. When the mass of metal, the core, is subjected to changing magnetic field, what they call eddy currents are set up in the metal that do no useful work, waste energy, and that kind of stuff. So they talk here about laminating the core to reduce the eddy currents. So that's not really all that crucial. Okay? However, the next thing is a little bit. Okay? If you remember, I said as the voltage goes up, the current goes down. So therefore, as the voltage goes down, the current goes up. So now our formulas, if you deal with the currents, you have to reverse things. And the book gives it this way, but you can reverse it any way you want to. IS, the way they put it, over IP. On this side, put the S on top, P on bottom, and on the other side, keep it the way it was. N sub P, N sub S. Now, I really don't like doing that to you. That seems like a crazy way to do it. How I would suggest writing it is this. IS times NS is equal to IP times NP. If you like that better, that's easier for me to remember. For voltages, it's the ratio. For current, it's the product. That to me is easier to remember. That, oh, we got to flip this, so they're both easy to remember. But anyway, whichever you want to use, they both work out the same. Because look at what your cross multiplying does. IS times NS equal IP times NP. So since you're going to do that anyway, why not let that be your formula? That just makes more sense to me. Okay? But you do it any way you want to. You paid your money, you take your choice. Okay, example 5. The primary current in a transformer is 10.0 amps. What's your, what represents primary current? What's the symbol? I sub P, okay? And that's 10.0 amps, okay? If the primary coil has 550 turns, what's the symbol for that? What's the symbol for that? Primary coil has 550 turns. N sub P, number of turns, and that's 550. Okay, is this the same one we have above? We don't know. Let's see. Not quite. And the secondary coil has 2,500 turns. So what would that be represented by? N sub S is equal to 2,500. Okay, with the first zero being significant. We're looking for the secondary current, I sub S. You give me a guess. Is that going to be a big number or a small number? Bigger than IP or smaller than IP? Well, you can let the math do the work for you if you don't want to do it yourself. Now, I like that second formula because it's just set up perfectly for you. NS is 2,500. Okay, I can write that first if I want to, times IS is equal to IP, which is 10.0 amps, times 550, if I could write, okay, turns. And then all we do is divide by 2,500. Okay? Well, first you might want to multiply those two together, and that would be 5,500. Okay? But however you do it, I sub S is that quotient. 5,500 divided by 2,500. A little bit more than 2. 2 point what? You need one more digit. 0, perfect. And that would be amps. Because you had 3 digits here, 3 digits there, 3 digits there, so this should be the 3 digits. I sub S is equal to 2.2. So it did go down because it goes in the opposite direction of the number of turns. And let's see what they got. 2.20 amps. Good for them. Okay? Now, I'm going to put these two together. Okay? And I'll do it on this page since I've got them all written on this page, but I'll put them in the middle because we're sort of combining, meeting in the middle here. So this gave us VP over VS is equal to NP over NS. And over here, they told us that NP over NS is equal to IS over IP, right? Going back to this one, okay? Now, let's take out the middleman, okay? And what do you have? VP over VS is equal to IS over IP. And since that's an inverse relationship, I don't like to use the ratio there. I like to use the product. And what does the product give you? VP times IP is equal to, not over, times. Yeah, VS times IS. And guess what V times I is? Power. This is the power in on the primary side. This is the power out on the secondary side. And they are exactly equal to each other. And that's what I was saying before. The power stays the same. Pretty much. Now, remember, just before this, we were talking about line loss, and there is some. There's loss to the lines, loss to the fluids, loss to the eddy current. So there are losses in there, but generally, the power in is equal to power out. Okay? So, ready to do example 6 then? And say, oh, okay. Okay. And sorry if it's written so crowded there. Deidre would be mad at me. She'd say, write down on newspaper, on clean paper. Okay. You see that? Okay.
So the one in the middle that you crossed out?
Yeah.
What's wrong with that?
That's NP over NS. See, NP over NS here, and it was also NP over NS down here. Same thing. And since we've taken care of these two, dealt with the number of coils, let's deal with current and voltage here. And sure enough, that gives us power in equal power out. Power on the primary side is the same as power on the secondary side. The voltage and the currents go down and up and up and down, but the power stays pretty much the same. Okay? Make sense? Kind of, a little bit, here and there. All right. Ready for the example 6? I'm going to stay on this page because this is our step up and step down transformers. So if it's okay, I'll eliminate the ink. Is that okay? Everybody got it? Okay. So let's do example 6. The power in the primary coil, what do we use to represent that? I just sort of gave you a new one. What the little kids do. PP. No. Yeah. Piece of P. Okay? Sorry, I didn't say that, did I? Okay, that's the power in the primary coil is 375 watts. What? What? Okay. If the current in the secondary coil, what would we call that? I sub S. Current is I, secondary coil is S. And they tell us that is 11.4 amps. Okay. What is the voltage in the secondary? So we're looking V sub S. Now wait a minute, folks. All you gave me was power in the primary coil, and here you're asking questions about secondary. How can we do that? I wish I had left some of that writing up here. What do we say about power in primary and power in secondary? They're equal. You don't create energy or destroy energy. Power is energy per unit time, same on both sides. So this is also P sub S. As soon as you know primary, you know secondary. Unless there's some loss in it, and you know there's loss. Wait, this thing is going crazy on me. Oh, man. It just turned itself off. So I'm going to have to bring it back up from current slide and go back to this, but none of my writing is on there. So, and now it lost the color of my pen. It lost everything. Okay. All right. We have P is equal to 375 watts. And later we said that's the same as PS, because you do not create nor destroy energy, and power is energy per unit time, so that stays the same. They told us IS was 11.4, wasn't it? 11.4 amps, and they're looking for VS. That's the unknown here. Now can we do that? Can we answer that question? What is VS? Does anyone remember the relationship between power, voltage, and current? We've said it a few times today already. It's right there. I wish they numbered their equations. That would make it so much easier. Look right above example 6. There's two little lines together, and then the line just above that says, or using P equal, you see that in the book? Just about the middle of page 534, above example 6, it says, there's a line just sitting by itself saying, or using P equal IV. There it is. So P sub S is equal to I sub S times V sub S. There it is. So P sub S, which was 375 watts, is equal to I sub S was 11.4 amps times V sub S. And that's what we're looking for. So how do we get V sub S? How do we get V sub S? Hint, these divide by 11.4 amps. By 11.4, both sides. You got to do the same thing to both sides, be democratic about it. Okay, this wipes out, and that gives you V sub S is equal to, pull out your handy dandy little calculators, and that's going to be something on the order of 3 point something, 3.5 or 6. Or is it 30 point something? 30 point something. Sorry. 30 something. Second? 32.89. 32 point, but we only need 3 digits, so that would be 0.9 what? Volts. Very good. Now, if you, did y'all like the triangles and circles we did before? Okay. Here's the one for this one. Which you prefer, triangles or circles? I don't care. Triangles. Okay. If we use a triangle, put the one that stands by itself, P, up here, and that's IV down here. So this time we were looking for V, so cover the V, and you have P over I, and that's exactly what we did. So voltage is equal to watts over amps. Amps equal watts over volts, and watts equal amps times volts. Okay. And they got 32.9. Also good for them. All right. Now they say at the top of the next page, 535, good transformers are more than 98% efficient. Very important in power transmission. It's impractical to generate electricity at high voltage, but high voltage is desirable for transmission. Therefore, you generate it at whatever is most convenient. Step it up with step-up transformers, which are very efficient. Send it across the lines. Then when you get into town that you don't want that high voltage, step down with step-down transformers and get it to people's houses. And usually there's several steps, if not on both sides, at least on the receiving side of that. So homework problems. Any of the odds? 1 through 25. They got quite a few to go on there. All right. All right, and then they have a little physics on the job, power distribution operators. If you're interested in that, you certainly can take a look. All right, now we're going to introduce a new kind of area. And let's see, anyone need this any longer? Okay. There was the last slide showing step-up transformers, leaving the generator before you send it out, step-up transformers, send it across at very, very high voltages. So in generating, they say typically around 6,600 volts. Transmit it, though, at 132,000 volts, very low current. That's what makes it more efficient. Step it down at the step-down substations to maybe around 6,000 volts. Send it to your home. That last little transformer up there on the power pole just before it goes to your house steps it down again to about 110 volts for your regular current, 220 for your high energy, high heat type things like hot water heaters, air conditioning systems, range, clothes dryer, anything like that, that gets to 220. Your regular stuff gets 110. Now, over in Europe, they do the regular stuff around 220 or 200, somewhere around in there, 240, somewhere in there. So when you go to Europe, don't take your the same charger that you do for your iPhones and stuff like that and try to use it there. You're going to burn something up because they use different things. So you can always buy a transformer for the transformer so that you can use your stuff. Okay? So that's the last thing in, what was that? 19.2. So let's discard that and go to 19.3. Well, where is it? Hey, you found me. I tried to hide. Okay, good. Thank you so much. Okay. I don't. Okay. I want to go from beginning, I think. Oh, why did you do that? That wasn't the beginning. So let's try that again. Okay. Ooh, there was what I wanted. So let's go back. I think it shut down everything. Let's go back to PHY112, 19, and now I put it back in order. I don't know what this thing is doing. Just doing whatever it wants to do. Okay. Let's see what the next slide is. No, this is not what I want. Is that the last slide in the whole chapter? I guess that's what they're saying. Yeah, there's a lot more to cover here. Now let me take, now that I've got a pause here. Okay. Chapter 19. We do 19.3, and if we have time, 19.5. Okay? So 19.3 is where we were. And since there's no slide there, we'll use this one from current slide. All right. Inductance. Electronic circuitry, and I don't know if you've ever looked in the back of one of the big old computers, or maybe even in the back of a television. I don't usually go there. You'll see that there's all sorts of stuff back there, but in televisions, radios, computers, electronic instruments, there are many components other than your little resistors. Okay? Those components include capacitors, inductors, diodes, and transistors. We're not going to go over all those. We're just going to focus on inductors and capacitors right now, if we have time to do them both. Okay? I've lost the word. Yeah, there it is. With those components, weak signals can be amplified, noise can be reduced, signals at certain frequencies can be detected, while at other frequencies rejected or eliminated, tuned out or tuned on or whatever, and everything cleaned up a lot. The analysis of the behavior circuits is pretty complex, so let's talking about the first, well, not the first one, but the one we're going to do in this section, inductance. Inductance measures the tendency of a coil of wire to resist a change in the current because the magnetism produced by one part of the coil acts to oppose the change in current in the other parts of the coil. And thinking back 2 or 3 sections ago, remember a coil of wire induces a magnetic field, right? And the magnetic field points in a direction that opposes the change in current, okay? So it's trying to keep itself pretty level. But remember, the currents are changing all the time in an alternating current, going back and forth, back and forth, back and forth, back and forth. So if you have an inductor, it tends to resist the change of current in that device. So an inductor is a current circuit component, such as a coil of wire, in which the induced EMF opposes any change in the current. Okay? EMF meaning voltage, induced voltage. Okay. The EMF is induced in the coil itself as the magnetic field of the coil changes. The unit of inductance, an inductor is, the unit of inductance is, yeah, I've got to change my pen back. Okay. Inductance, whereas resistance is R, voltage is V, current is I, inductors are, the symbol for that is L. Okay, that's the parameter, L, for inductance. This is a measure of inductance. Okay? Now, the unit for that is the Henry, H. Okay? H is the unit, named after Joseph Henry. I believe he was an American, born in Albany, New York, physicist, constructed the first electromagnetic motor, discovered electric induction, demonstrated blah, blah, blah. So pretty important character there. Now, let me remind you of something. What was our unit we used to refer to frequency? You remember? Hertz. And we had to use HZ. Why did we have to use HZ? Because the H was already occupied by the Henry. So that's why Hertz is HZ, whereas Henry is just H. A coil has an inductance of 1 Henry if the EMF induced is 1 volt when the current changes at the rate of 1 amp per second. Okay? Now, that seems a little bizarre, but here's what 1 Henry is. 1 Henry is not that silly little cartoon character, that's not what we're talking about, is equal to 1 ohm second. 1 ohm second. So it's a resistor times time. Okay? The Henry is a large unit, typically. More practical units are the millihenries, which would be mH. You don't run into henries all the time. You don't want to. They're too big. So you deal in millihenries most of the time. 1/1000th of a Henry. Like a millimeter is a thousandth of a meter. The thickness of a dime as opposed to a meter stick. Okay? Inductance can be illustrated by connecting a coil with a large number of turns and a lamp in series. When connected to a DC source, the lamp burns brightly. Okay? However, when this current is connected to an AC source of the same voltage, the lamp is dimmer because of the inductance in the coil. Okay? So, and by the way, remember a resistor was represented by a jagged line. An inductor is represented by a coil, because it is a coil. Okay? I don't know why they did jagged line for a resistor, except it puts a lot of resistance in there. Okay. Now, they're going to come up with a new term here. And this new term is called inductive reactance. Okay? Now, inductive means it comes from an inductor. Okay? Reactance means it kind of acts like a resistance. In fact, it has the same unit, which is an ohm. Okay? And the inductive reactance is given this symbol. Reactance is X. That's the reactance part. Inductive means X sub L. That's the inductive part. Okay? Okay? And what we have there, sorry, I've got hiccups, is equal to 2 pi times the frequency times the inductance. Now that's not length, that's inductance. Now let's think about what we've got here. 2 pi is just a number. 2 is a number, pi is a number. Frequency is measured in 1/2. Remember? Cycles per second, Okay? And inductance is measured in ohm seconds. So your seconds cancel out and you're left with ohms. So the reactance is like a resistance. Okay? Only it's the inductive reactance, the resistance that is produced by an inductor. It's not the same as the resistance produced by a resistor. That's just heat loss usually. It's the resistance that's produced because of the inductor as being there. Okay? So X sub L is the inductive reactance, alpha is the frequency, expressed in hertz, such as 60 hertz, 60 per seconds. That's your common, everyday household frequency, is usually around 60 per seconds. Okay, 60 hertz. And your L is inductance in henries. But remember, a henry is a huge unit, so if inductance is given in millihenries, the conversion must be made to henries to make the formula right? So, the current in a circuit that has only AC voltage source and an inductor is then this. Current is equal to E, which is the voltage, divided by X sub L, which is the inductive reactance. But remember, that acts like a resistor, and I is equal to E over R, right? But in alternating current, because of that alternating current, this coil creates some resistance because, say, if the current is flowing this way, the resistance is this way. You set up a field in the opposite direction, which acts like it's impeding the flow. And actually later we'll call it impedance. They have 3 different words for almost the same thing. Resistance is from a resistor, and inductive reactance is from a inductor. Okay, I'm losing my words here. All right, let's see if we can work example. See, all it says is example 1, I guess. So can I clear this screen so we'll have room to work? You've written down the formulas, right? Of course you have, okay? A coil with a inductance of 1.0 millihenry. So what symbol do we use for inductance? Inductance? L. L is equal to 1.00 millihenry, okay? Is connected to a 60 kilohertz AC power source. So it's, what does kilohertz measure? What does hertz measure? Frequency. So this is 60.0 kilohertz. Kilohertz. There we have our henries and hertzes, okay? And that's AC power. And what's the voltage on that? V is equal to 110 volts. Okay. What is the current in the circuit? So we're looking for I, the unknown here. Now they say, draw you a picture, which is almost always a great idea. Now, here's a little bit of difference though. When you have AC circuit, we usually represent the power source as a generator. Not that there's a real generator there, but that's where you plug it in, that's what you get. Whereas DC, we usually represent as a battery. That's not really a battery, but that's what it looks like. So this is DC, this is AC. Okay? So you're generating a voltage here, and that's 110 volts. The E is equal to 110 volts. That's what they told us here. And that goes into the circuit, and the only thing you got in this circuit is an inductor. Okay? And this inductor is 1.00 millihenries, because a henry is a huge amount of inductance. Okay? Now, the frequency here is 60.0 kilohertz. They just threw that in there. Alpha is equal to 60.0 kilohertz. All right. Now, what are we going to do with that? We're looking for current. I is what we're looking for. Now, we draw it like this, okay? Knowing that current isn't just flowing in one direction. It's alternating current. It's going back and forth, back and forth, back and forth. But we draw it as if it's just going in one direction, just because that's how we used to draw it. All right. What was our formula for current? Do you remember? I is equal to E over what? R was if it's a resistor. What do we use if it's an inductor? The thing that's equivalent to resistance. X sub L. Inductive reactance. Yeah, okay. Later it's going to be called something else, and I always get confused which one we're calling it now. Later we're going to call it impedance. So, if we get that far. I don't think we will. Okay? But we got to get X sub L. We don't have X sub L. We got E right there. I put V, but they are calling it E. So we got our E, but we don't have X sub L. So let's go back and do what X sub L is. What is X sub L? They gave us that before. 2 pi frequency times inductance, L. Okay, we've got frequency, we've got inductance, we got 2 pi, so we can go to town on this one. Except that our inductance is in millihenries, we need it in henries. So what is that going to be? 1.00 times 10 to the milli means minus 3 henries. That's it exactly. Oh, and by the way, we need it, the frequency in hertz, they give it in kilohertz, so what is that? 60.0 kilo means times 10 to the third hertz. Okay? And he's not the Alabama quarterback, by the way. Okay. Now, so this we can plug in. We got 2 pi times 1.00 times 10 to the minus 3 henries, okay, times inductance of, no, I put it backwards, sorry. I thought something looked wrong there. I started to put HZ, and I thought, where's my Z here? Okay. The frequency is 60. Now, this isn't scientific notation, but I'm writing it the same way they do. Times 10 to the third hertz, okay, times the L, which is your inductance, 1.00 times 10 to the minus 3 henries, okay. That's going to be our inductive reactance. Okay, I got it right that time. All right. Now, let me give you a hint here. Rather than punching all those numbers, punching numbers doesn't hurt. But here, 10 to the third times 10 to the minus third is 1. Because 1 is 1,000 and the other is 1,000ths. So one is times 1,000, the other is divided by 1,000, so they go out to 1. So now all you've got is 2 times 60 would be 120 pi done. And that 0 over the 120 is correct, is significant. So that's going to give you, and this will be, in what units? A hertz is a per second, 1 over second, and a henry is an ohm second. So the seconds go out. This is in ohms. Same unit as resistance, like you were saying, but there actually is an inductance now, not a reactance now, not a resistance. Okay? Now, we can take that and put it under, our E was 110 volts, divided by 120 pi ohms. And guess what? Volts divided by ohms are? Amps, exactly, and that's what current is measured in. So everything's looking pretty good. I would say that's going to be something close to 0.3, give or take a little bit. You tell me. (110) divided by 120 and then divide again by pi. Or you can put 110 divided by open parentheses 120 times pi, close parentheses, that works too. I like to just do 110 divided by 120, then divide that answer by pi. What do you get? 29. Oh, look at that. One more digit. Say again. 290.
Well, the answer is like 0.291.
1. Okay. 17? Okay, that would be 292. Wouldn't it? Because the 7 bumps it up by 1. Okay. 292 amps. How did they? Oh, look at that. They got it right too. 0.292 amps. Okay. Now the interesting thing here, and I wish they had this slide here, but I don't think it's essential for what you're doing, but maybe it is. I don't know. Can I go on and delete this? Actually, I'll just go to another slide. I'm going to this slide and try to show this because it's already in a graph for me. If the voltage, and remember AC voltage is it's alternating always. So let's take it up about to here, okay, and down to here, and down to what they go up for. Oops, let me do it. Let me clear that. Okay, start here, go up here, down here. Whoops, one more down, up. Then I probably didn't do this. This is your voltage. Yeah, okay. That's what it's doing all the time. Okay. Now, in an inductor, the current lags behind the voltage by 1/4 of a cycle because of the inductor being there. Remember, the inductor is resisting the change in current, so it gets behind. So therefore, the current is doing something like this. You see, if you had carried this voltage on here, it would have been coming from here. Well, that's where the current is here. So I'm going to move the current up here to 3 blocks. So it's here. It goes up to there. It goes up to there and down to here and down to there and up to here and down up to here and down to there. Let's do that in red. Is that okay? So the current is doing something like this. Remember, alternating current is alternating up and down. And that's what your current is doing. The black is the voltage, your E, and the red is your current, I. Okay. So it lags by a quarter of a circuit. One complete loop is 2 pi, or 360 degree. A quarter of 360 is 90 degrees. So the phase on your current is 90 degrees behind the phase on your voltage when you have a single inductor in the system. So, homework problems here would be any of the odds 1 through 5, and then do some of the odds 7 through 11. Okay? Now, there is another little interesting blurb here on ground fault interrupters. Any of you ever seen one of those? You have, whether you realize it or not. I wish there's a picture in the book, but if you don't have it, it's those plugs that you usually have in your bathrooms and your kitchens and outdoors where there could be rain. You know, anywhere that's likely to be water, it's a plug that's the size for the plug-in is about the same, but there's a little space in between. That's where your ground fault interrupt. It has a red button that says, I think one of them says reset and one of them says something else. One is test and one is reset or something like that. And what happens is, if you ever, I don't know if y'all remember this, the old mystery shows, one of the favorite ways to knock off the spouse or the girlfriend or the guy friend or whoever it was that you didn't want anymore, wait there in the tub and then drop in a hairdryer, okay, with it plugged in. Turned on, yeah. Well, with ground fault interrupts, that doesn't work anymore, okay? They watch too many of those things and say, what can we do? Well, what happens there, as soon as it detects that there's a sudden change, the inductor reverses that and pops the button. So that's what a ground fault interrupt does. And you'll see them in kitchens, bathrooms, and usually outside plugs, okay? Look for them. You'll find them. Hopefully. If not, you might want to consider not being there anymore and going to a safer place. Never mind, I'm just kidding. All right, now I wish we did 19.4 because that's inductors with resistors, but they don't. Okay? We go on to 19.5. Let's see how big of a problem that. Oh, it's only one page. How much time do we have? The clock's not working. We have as much time as we need, right? All right. I have a watch somewhere here in my pocket. My pen broke, and I haven't found one to replace it yet. Well, we got 10 minutes. Let's see what we can do. Now, I said before, there's another word coming up that sounds like it means the same thing as two other words. And that word is impedance. It's a measure of the total opposition to current flow. Okay? In a resistor, the opposition is called resistance. Okay? In an inductor, it's called reactance. It's reacting to the current flow. When you combine the two of them together, it's called impedance. It's impeding the current flow. So, yag. That's why it's so hard to keep up with which is which. Impedance is a measure of the total opposition of current flow in an AC circuit resulting from the effect of both resistance and inductive reactance. And in the next section, we'll find out capacitive reactance. There's yet another reactance, but it's just called reactance. Okay? And here's what the, okay, let me go back to my slide. Clear this out of the way. Okay. For a resistor, the resistance is R. Okay. For a capacitor, the resistance is X sub L. and we won't go into it. Okay. Both of these are measured in ohms, remember? This was frequency times inductance, but inductance is an ohm second, frequency is a per second, so that comes out in ohms, that comes out in ohms. Well, the new one is going to be impedance, and I'm just going to write down the word impedance, okay, or at least part of the word, and that's measured, the symbol for that is Z, okay? Now, Z is also measured in ohms because resistance and capacitance is measured, resistance and inductive reactance are both measured in ohms, so Z is measured in ohms, and that will be, so our new formula in AC circuits for current is really E over Z. Now, if all you got in your circuit is resistors, that's just all your resistors, okay? It's R. If all you got in your circuit is inductors, then it's just X sub L. But if you got both inductors and resistors, and later capacitors, if we get that far, then it's going to be Z. Okay. What is Z? Remember, that last thing that I did, that the currents and the voltage are out of phase. Well, in order to make those work, what a Z is the square root of R squared plus X sub L. How an L became a 4, I don't know. X sub L squared. Okay? Now, I don't know if y'all, that rings a bell or looks sort of familiar, but what you get from that is, that looks like good old Pythagorean theorem, doesn't it? Where R is one leg, L is another leg, and Z would be the hypotenuse. That's exactly C squared. C is equal to the square root of A squared plus B squared. That's exactly the same type place that comes from. Okay? Now, since we know that X sub L, R is just R, is actually 2 pi F L. Remember? Square that, okay, and put it in your pipe and smoke. No. If you don't know the X sub L, you can, but you do know the frequency and inductor, which is usually what you know. You know the frequency, you know the inductance, so plug those in rather than using X sub L. Okay? Does that mean we're getting close to leaving time? I guess we're going to have to stop here, sadly. Okay, first thing I want to do is give you your final test, the last test. Okay? Now, here it is. But also I want to talk with you about one. Nice one. Okay, you can put the credit. Okay.
Is this the same one?
Huh? Oh, yeah, you got it last time. You didn't get it last time, did you? Okay. I can give you yours. Did you get one last time? And you did get one. Okay. All right, let me show you how many questions you have to do if you're interested, or you can do them all. Okay, we did 1, 2, 3, 4. Okay, the first 3 I know were from chapter 18. Okay, that's the magnetic stuff. Oh, I think maybe 4 is 2. Yeah, 4 is 2. But then, number 5 is from this chapter, chapter 19. Okay? And 6, 7, 8, and 9 is from this chapter. Okay. Except you can only do the A part, because the A part uses this formula right here. The B part, the phase angle, we didn't get to. But you can also do the current. Because the current, you do this form. Okay? So in 9, you can do A and C, skip B. Unless you just want to do B, that could be extra credit. Bonus, okay. And then number 10, we didn't get to do it all, so that's going to be bonus, or you can leave it blank. It doesn't matter. Leaving it blank or missing it will not lose you any points. Getting it right will gain you a point or 2. Or so, well, 1 usually. Okay. Now, that's the test. Now let's talk about when to turn it in. Okay, you've got it now. If the Bessemer campus is more convenient to you than this campus is, let me tell you the hours I'll be on Bessemer campus on Monday. I have regular classes 8 to 10:40 and 11 to 1:40 on the Bessemer campus in Building A. My classroom is 255A. But since I'll be teaching, if you want to just slide something under my door, you can go to my office, which is 265 in the A building. Okay? And y'all almost have to know that building to know how to get around, but you can probably figure it out. So that's Monday. Between, say, 2 and 6, I'll be in my office or somewhere around my office. But if I'm not there, if I'm in the restroom, something like that, you can slide it under my door. Okay? Now, that's Monday. Tuesday would be the earliest, really, that this would be due. But if you finish it early, you can turn it in early. Okay, Tuesday, I'm on the Bessemer campus in my office, 265, A building 265, from 7:45 in the morning until noon. At noon, I'm in my classroom, 255, I'm giving an exam. Okay, I'll be there. I doubt if I'll be there 2 hours, but whatever it takes, I'll be there around 2 hours or less. Okay? So if I'm up there and you just want to slide it under my office door, you can. Don't ever slide it under a classroom door. Make sure it's my office door, 265. Okay? Then I'll be back in the office Tuesday afternoon until 3:30 when I come over here. So between 4 and 6, I will be here. I'll be grading papers. I'll be entering grades. I'll be doing attendance. I'll be doing email. I've got plenty I can work on my computer here. I'll be here 4 to 6. If this is more convenient for you, you can do that. If you don't have it ready on Tuesday, Wednesday, I'll be back on the Bessemer campus. I have no finals then, so I'll be there from 7:45 in the morning until 6 in the evening. All day Wednesday. Thursday, same as Tuesday, except no final that day. I'm on the Bessemer campus from 7:45 in the morning until 3:30 in the afternoon. At 3:30, I leave to come over here. I'm here 4 to 6. So you can either get it to me there or bring it here between 4 and 6. Now, if the class time is not convenient for you next week, and on Tuesday, Thursday, if you need to get it here before I'm over here, give it to who's that strange lady in the office? Okay, Miss Murphy in the office, and she will be glad to give it to me when I show up. Okay, I'm pretty sure she will. Okay. And I can't speak for her. Okay, so that's Thursday. The college, even though it's in August now, the college is not open that Friday. The first Friday in August, we are not open, so don't be leaving anything anywhere. You can't get in the buildings on Friday. So get everything in Thursday. Now, if you can't get it to me on Thursday before 6 o'clock, you can take it to the Bessemer campus and slide it under my door as long as the building's open. And when I get in on Monday morning, it'll be there and I can grade it. I'd rather you get it in Tuesday through Thursday. Okay? That would be far superior. Okay? But I will take it. I'll grade it if I can. If I get it too late, you're getting incomplete, because I have to have grades in by 12 o'clock noon. Okay? Then, if I get it in late and I then have time to grade it, then I'll change the I to your letter grade probably the same day. But Monday's the last day I'm there, I think. So anything after Monday is going to be once we get back in the fall. Okay? Which, is about a week and a half or 2 weeks or something like that. So, one more thing. Y'all told me student course evaluations did come out either late last week or earlier this week, so please do your student course evaluations. Okay, I want to hear your feedback, things I can do to improve. This is only second time I've taught before, so I don't know if it's the best way to teach or anything like that. So y'all let me know. I mean, I won't know who said what, I get the positive. But if I see a lot of negatives there, I'll try to think of things I can do better. Okay? So please do the student course evaluation. Anything else? Can't think of anything. Been an enjoyable class. Y'all have been great. This group has been really good about being here. A few of the others have been great about being here too. A few of the others, I think I remember how they look. No, I don't. Just kidding. Okay. So good deal. Any questions? All right, good deal. Then let's have a good weekend. Working on physics will make it good, right? Sadly, it'll be the last time you'll be doing this for a while. Okay. All right, good deal. I'll see if I can. Okay. Yeah. Let me get things shut down. No reason wasting the bulb. Oh, it's shut down. Okay. Oh, hey. All right, you found me. Good deal. Thank you. Oh, my goodness gracious. Let me get